Well, now that we know this, what else can we do? Well, we could start by looking at fractions of a circle. So, for example, let's take half a circle. How many radians are there at the center of half a circle? Okay, so half a circle, something like this. Here's the center of the circle, and here are the two radii. What's this angle at the center here? Well, we know that 2 pi radians equals the whole circle. So if we want half the circle, then we take half of 2 pi, which is pi. So there are pi radians in half a circle. Similarly, if we want to just take a quarter of a circle, well, this would be a right angle. This would be, well, we can just divide by half again to get a quarter of a circle, and we see that this is pi over 2 radians in a quarter circle. Well, this brings to mind an interesting question. I mean, you're probably quite used already to measuring angles in degrees. And you probably know that there are 360 degrees in a circle, 180 degrees in a semicircle, half a circle, and 90 degrees in a right angle. So how can we convert then between radians and degrees more generally? Well, let's just start by writing out again what we've just seen. We saw that 2 pi radians equals 360 degrees, and that pi radians equals 180 degrees, and pi over 2 radians equals 90 degrees. Well, if we want 1 radian, then, well, we can start from this equation, and if we divide both sides by the number pi, then on this left side we get 1 radian, on the right hand side we get 180 over pi degrees. Well, if you work out what this is on a calculator, you see that this is about, 57 degrees approximately, which is pretty close to 60 degrees. And it turns out that 60 degrees is the angle between two hands on a clock when the time is 2 o'clock. So if we take one of our sections before, which is 1 radian, and put it on, and let's see how this goes. And we see it's pretty close. It's a bit less than 60 degrees, which is what we expect. It should be about 57 degrees. So everything seems to be matching up pretty well here, and we can be pretty sure that we're correct. If we look at this formula that we just got, then maybe we can see how to use that to convert radians into degrees and degrees into radians. Well, if we rearrange this formula, 1 radian equals 180 over pi degrees, we can see that we get pi over 180 radians equals 1 degree. And we can use this to work out how many radians there are in any number of degrees. For example, let's suppose we wanted to know what 45 degrees is in terms of radians. Well, we multiply the right-hand side by 45. Let's multiply the left-hand side by the same thing. And this 45 goes into 180 4 times exactly, so this is pi over 4. So we see that pi over 4 radians corresponds to 45 degrees. Well, thinking back to our right angle, we know that this was 90 degrees, and half of that is 45 degrees. We also know that the right angle was pi over 2 radians, and half of that is pi over 4 radians. So everything is matching up very nicely here. Another question that we can ask is, well, let's suppose that we have a circle and we have 2 radii at the center of the circle making an angle, some angle theta. How long is the arc length between these 2 radii? Let's call it L for length. Well, let's start by looking at this angle at the center, theta. What fraction of a total circle does this angle represent? Well, we know that there are 2 pi radians in a circle, so if we take theta divided by 2 pi, this gives us the fraction of a total circle here that we have with this angle theta. Let's check this with a simple example. If theta was equal to pi, then we'd be back in this situation we had here, and we would see that theta divided by 2 pi, so let's say theta equals pi, then theta over 2 pi is pi over 2 pi, which is a half. So we would have half a circle, and that's exactly what we see we do have here. But look, in this case, we've got half a circle in terms of the angle, but we also have half of the circumference. The arc length here is half of the circumference as well. And this is going to work in general. The length of the arc that we have here, as a fraction of the total circumference of the circle, is the same as the fraction that theta is of the total angle at the center of the circle. So in other words, this fraction, theta divided by 2 pi, is going to be equal to the fraction that is given by the length relative to the total circumference. Okay. Now if we rearrange this formula, we see that the length is equal to the circumference multiplied by theta over 2 pi. But we know that the circumference is given by 2 pi times the radius. So substituting that in, we get this formula, and then cancelling the 2 pi's, we see that the length is equal to r theta. Now how nice is that? Well, do we believe this formula, that the length is equal to the radius times theta? Let's check. Let's imagine that we fix the angle theta and we look at a larger circle, so we increase the radius. Well, if we have a larger circle, then we would expect the length to get larger as well. So that makes sense. What about if we fix the radius? So we have the same circle, but we change theta. Well, if we increase theta, the length will get bigger. If we decrease theta, the length will get smaller. So everything seems to be matching up very well. Okay, so now we've seen what a radian is, and we know why there are exactly 2 pi radians in a circle. We can convert back and forth between degrees and radians, and we know how to work out arc lengths. But you might still be wondering, what's the actual point of radians? I mean, degrees are easy enough. Why don't we just stick with them? One answer to this question is precisely this formula that we just derived, L equals r theta. For this formula to work, it is essential that this angle must be measured in radians. If you measure the angle in degrees instead, the formula gets much messier, and I'll leave it to you as an exercise to work out what it looks like in that case. Now, there are other, more important and deeper reasons that we use radians instead of degrees, but they'll have to wait until later in the course when we learn about trigonometry and calculus.